and welcome to our today's lesson, where we are going to be looking at forces. Forces is one of the topics or the areas that we have in physics, which will provide most of the questions that you have been having about nature and what happens around you. Probably the question that we should start by asking ourselves is, what is force? What is force? What is force? Sometimes you could be having a few definitions in your mind that you have come across in the course of your research in an endeavor to find out what force actually is. And I will start by defining force for you so that probably we can go ahead and conceptualize this whole idea of force and what it can do for us. I will give you a very simple definition for starters, and I want to define force as a pull, a push, or even a twist upon an object. It is actually a pull, a push, or even a twist on an object. Now, it depends with the kind of force that you apply on something. That is when we can classify it as either a pull, a push, or even a twist. Take, for example, you want to elongate this spring balance here. You need to pull it like that, so that now the length can be elongated. The same case applies when you want to shorten the length of your elongated spring. You will have to push it. You will have to push it. And sometimes, if you want to squeeze water from a piece of cloth, you will have to twist. Now, in all those cases, you are actually applying a force on an object that you are actually working with. So, any type of force that you will come across and which we shall look at shortly could either be classified as a pull, a push, or even a twist on an object. What can force do for you? Why should we understand this concept of force? It is because in nature there are a few things that force can be able to do for you. In nature, force causes virtually all the movements that you can think of. For example, when you want to walk, there is a force that is supposed to guide your steps and ensure that you maintain your balance. If you are running and you want to halt, there is a force that should help you to stop. When a car is running, there is a force that should be applied to brake it, and so on and so forth. However, it should not be misunderstood. It is not every time that you will apply a force on something that it will result to a movement. Let us look at effects of force of force, so that probably we can manage to get the idea clearly. One of them is change of motion of an object. Change of motion of an object. And under this, I want us to look at two situations. And situation A is a situation where a body is at rest or moving at a constant speed. Force can be able to start or accelerate an already moving object. It can actually start or accelerate an already moving object. By accelerate, I mean you increase the speed of the moving object. Now, that is one of the effects that force can have on the motion of an object. That if the object is at rest, force can be able to trigger motion of that particular object, or even increase the speed of the moving object. Under change of motion, you could also be having another situation where a body is moving and you want to slow it down or even stop it. Force will help you slow the moving object or even stop it. So under effect number 1, we look at change of motion of an object, and we say that force can actually start or even accelerate a moving object. A force can also slow down or even stop a moving object. Now, there is a certain word that we are going to give to this effect of slowing down a moving object, and that is what we call decelerate. Force can decelerate a moving object. If you say decelerate, what you mean is actually that effect of slowing down a moving object. Now, let us look at effect number 2 that force can have on an object, and that is what I will call change of shape of an object. Change of shape of an object. Remember, we said that force is a pull, a push, or even a twist. What will happen to this box if I push it, for example? Just look at that. By applying a push on this box, you actually distort it. But when you release it, it regains its original shape. That is an effect of force. It is actually changing the shape of our box. Now, look at this piece of cloth that I have here. I can decide to twist it. If I twist it, I'm actually changing the shape of the piece of cloth. But I can decide to release it so that it can regain its original shape. The same case would apply if you pull a spring. If you have a spring like this one and you apply a pulling force, what happens is that the length is going to increase, and consequently we can claim to have distorted the spring. Effect number 3 is the change of direction. Change of direction of an object. Change of direction of an object. Again, let us come back to this box of ours, and we assume the box is moving towards this direction, and we apply a force to the other end. What will happen is that we will change the direction of movement of the box. That is an effect that can also be brought about by a force. Now, having talked about the effects of force, I will want us to classify our forces into different classes so that we can come up with the different kinds of forces that we can have in nature. And that one is going to be guided by how the particular forces operate. Let me expound on that by giving you the different kinds of force before we can even think of how we can classify the different forces that we know. And number 1, or class number 1, is what we are going to call the contact forces. Contact forces are those forces that will require that a body comes to contact with them, or that the body that is going to be affected by the force actually touches with the force that is going to be applied. So we can define them as the forces that influence only those bodies that they are in touch with. We said in our definition that a force could be a pull, a push, or even a twist. Let us think of the force that we applied to distort this box, which we are going to call the applied force. Now, we had to bring our hands into contact with the box so that we could push it and distort it. Suppose our hand is not in contact with the box. How then can we apply the force to distort the box? It means it has to come into contact with your hand, and then you apply the force that will distort your box. That one is an example of what we call a contact force. I will want to give you examples here. And examples of contact forces include, number 1, what we call the applied force. The force that you apply so that you can have an effect on a body is an example of a contact force. Let me give you yet another example, which I'm going to call friction. Number 3 is buoyancy. Buoyancy. And number 4 is the normal force. You can add onto the list the types of forces that you know if you think they fit into that. We shall look at a longer list later in the chapter. Now, the next kind of force that I want us to look at is what we call the non-contact force. Non-contact force, or what we call the field force. Non-contact or the field force. Now, non-contact forces are also called the field forces. Now, these forces will act on an object without actually touching it. That is why we call them non-contact, because the body needs not come into contact with the force for it to experience the effect of that particular force. So we define it as the force that acts on objects without coming into contact with them or without touching. But the touch is not there, but the force will still influence that particular object. An example of such forces is what we call the magnetic field. Magnetic field force. Now, magnetic field force is actually experienced by bodies that are brought close to a magnet. Remember, we are saying close, but not necessarily touching the magnet. Now, why do you think a body would experience the force even without coming into contact with it? Now, that brings us to the question of the field. The field that we are talking about. And the field, it's worth noting that the field is the region around a force where its effect is felt. That around a magnet, for example, there will be a region where the effect of that magnet will be experienced, even though the body does not come into contact with the magnet. And that is what we call the magnetic field. Now, something interesting you will note about magnets, like the one I have here, is that it has two ends. A magnet has two ends. It has this one and this other one. Now, end A of this magnet is what we would call the North Pole. Why the North Pole? Because it is actually indicated with an N. The other one automatically becomes the South Pole. Now, we have our bar magnet, like the one I'm holding here. Sometimes it could be painted like this, but you have an indication of a letter N and probably another one, S. Now, the end that is indicated N is what we call the North Pole. The North Pole or the North Seeking Pole. Now, the other side that is indicated S is actually the South Pole, or what we would call the South Seeking Pole. Now, those are the two ends we have in a magnet. Now, there is a rule that guides the operation of this field we are talking about as being called the magnetic field. Which touches on the two poles of a magnet. We are saying that the ends of the magnet are actually called poles, where we have the North Pole and the South Pole. Now, we said that a region around a magnet that we call a magnetic field is the region where the effect of that particular magnetic effect is going to be felt, even though the body does not come into contact with the magnet. Now, take our bar magnet, for example. We are saying there will be a region around it. If you place a magnetic material anywhere in this region, it is supposed to be influenced by that force that we are calling magnetic force. Look at this iron bar, for example. Now, we bring it close to a magnet, but not necessarily touching it. What is going to happen to it? You will experience a pull on the bar, and eventually the bar is going to be attracted by the magnet like this. So when the bar is brought close to it, you can experience a pull, but if you bring it into contact, it's actually going to be attracted. Now that is what we are talking about as being the field of the magnet. Now, it is not all the time that you bring a magnetic material close to a magnet that is going to be attracted. There is a law that governs the operation of the poles of a magnet, which we are going to call the law of magnetism. And the law of magnetism simply states that like poles repel while unlike poles attract. Now, repelling is an example of a push, because something is being pushed away from another one. That is why we say it is being repelled. On the other hand, an attraction is a pull, because an object is actually attracting another one towards itself. And from the definition of force, we said a force could be a twist, a pull, or a push. That is why magnetism qualifies to be a force. Now, let us think of what will happen when we bring the north poles close to each other. Like the two bar magnets that I have are indicated north. I bring the two knots close to each other and we look at what happens. What happens is that no attraction is realized. How about if I reverse the poles of one of the magnets? You realize that attraction is realized. The same case applies if I would reverse this other one. When different poles are brought close together, attraction is realized. Suppose I bring the south poles together, no attraction is going to be realized, which helps us to demonstrate that actually like poles attract while unlike poles repel. Now, around the magnet, there are lines of force, along which magnetism or the magnetic force operates, and that is what we call the magnetic lines of force. Magnetic lines of force, which we are going to demonstrate using iron filings. There are those lines that are formed by the iron filings, which have been sprinkled within the region that we are calling the magnetic field of this particular bar magnet. You can look at the arrangement. There are some straight lines that are assumed by those iron filings. It is worth noting that at the poles, that is where we have the highest concentration of the iron filings that we are using, and I will tell you the reason right now. It is because the field is strongest at the poles and lessens in other regions around the magnet. That is why we have concentration of iron filings being dense on on areas around the poles and lessening towards the other regions of the bar magnet. Now, these particular lines are what we call the magnetic field lines, and they are the lines along which the magnetic effect is felt. Let us look at characteristics of magnetic field lines. Number one, characteristics of magnetic field lines. Number one is that they are more concentrated, or we can say they are close to each other at the poles and gaps out in other regions. We look at the pattern that we are having here. Again, we can be able to see that at the poles we have more ion filings, and towards the other regions the density lessens. That is what we are talking about. The arrangement of the ion filings at the poles is close to each other and lessens all other. They gap out as we move away from the poles. Now, another thing we have to note is the reason as to why the ion filings behave like that, and it is actually because the field is stronger at the poles, and weakens as we move away from the poles. As we move away from the poles. Now, characteristic number two is what we will call the law of parallel lines, where you will note that the field lines are actually parallel to each other and never crosses each other. They never cross each other. Now, the third and last characteristic is that they originate from the north to the south pole. They originate from the north to the south pole. Now, just so you can understand the concept of how these lines operate, I want us to look at a few patterns that you can come up with when different poles are brought together. And we are going to call them magnetic field patterns. Magnetic field patterns. Magnetic field patterns. And we start with the one that we have just demonstrated of a bar magnet. Again, remember, we said we have two poles. We have the north and the south pole. We said that these lines originate from the north and to the south pole, like that. They are actually originating from the north to the south pole. It is good to note that my arrowhead points from north to south, which indicates that they are originating from north to south pole. Again, note the distance between individual lines at the poles and in other regions. You see that in other regions, the lines are actually far apart as compared to near the poles where they are concentrated together here. Now, there is also another arrangement that we can try and investigate where we have a north and a south pole brought close to each other, a north and a south pole of different magnets brought close to each other. Let's see what will happen to our ion filings and the pattern that is going to result from that. Again, we have our field lines originating from the north to the south pole, like that. Remember to indicate the direction of the lines using an arrow. It's very important, like that. They originate from the north and to the south pole, like that. How about if we brought two poles together that are like? Remember we said that like poles repel while unlike poles attract. So what will happen when we bring two poles that attract, that are like, close together, that repulsion is going to be realized, so that now your lines will behave like this. Remember, we have a north, so they are originating from the north and seeking the south pole. Again, from the other magnet, they originate from the north and they seek the south pole. So around this region that I'm going to mark X, there will be zero field. If you look at our diagram, no line crosses this region. That means whatever you place at this region that we are marking X is not going to experience the magnetic force that results from this magnet or even the other magnet. And for that reason, we say that the field at region X is 0, and therefore we call it the neutral point. At the neutral point, whatever material you place at the neutral point is not going to experience any magnetic effect of these two magnets, because there is no line of force that crosses that point. Now, the same case will apply if you had south poles brought together. South pole. Now you will have lines that originate from some north somewhere and towards the south pole. Note the direction of the lines of force. It is now changing, and you will have again other lines originating from a north somewhere and towards the south. Remember, we said that the magnetic lines of force will always originate from the north to the south. Therefore, that is why our arrowheads point towards the south. Again, you will have another region X where there will be 0 magnetic field, and it is also referred to as the neutral point. So regardless of the poles that you bring close together, so long as they are like, there will be a neutral point somewhere at the middle of the field that will result. Now that one was one example of a field force that we have just looked at, and we have seen that there are patterns that will result from the different poles that can be brought together as they interact. Now, is it every material that you bring close to a magnet that is going to be attracted? You can try a set of materials. For example, you can work with your pen. You can bring your pen close to a magnet, see whether it is attracted or not. You can try something else like a piece of wire, bring it close to a magnet, see what happens. You can also take a piece of paper, bring it close to a magnet and then you note what happens. You will realize that actually not everything that you bring close to a magnet is going to be attracted. For that reason, I want us to classify materials And our classification is going to be based on the effect that a magnet has on that particular material. You will realize that you have a class of materials we are going to call magnetic materials. Magnetic materials are actually those materials that are attracted by a magnet. We define them as materials that are attracted by a magnet. An example of a magnetic material is what we call iron. We have worked with iron filings and we have seen them respond to a magnet. That is what we call magnetic materials. They can be attracted by a magnet. Another example is steel, and the list can continue. Another set of materials are what we will call non-magnetic materials. And non-magnetic materials are those ones that are not attracted. They are not attracted by a magnet. Non-magnetic materials are those materials that are not attracted by a magnet. And an example is plastic, like your pen, plastic, rubber, wood, and the list can continue. Now, remember we are still looking at field forces, and I want to introduce another field force that is very much related to magnetic field force, which we are going to call electrostatic. Electrostatic field force. Electrostatic field force is actually electrostatic field force is a force that is felt by objects that are brought close to static charges or motionless charges. That is what we call electrostatic field force. That it is a force that influences objects brought close to motionless charges. A very simple example is when you rub your pen on your hair. You can do it. Let us try that. That you rub your pen on your hair. Now that is an example of an object that has acquired static charges. Static charges are what we are calling motionless charges. That means if you twist your pen to the other surface that had not wrapped your hair, it is not going to have the same effect because the charges do not shift. That is why we call them static charges. Now, these static charges also are of different types, depending on the material you use to wrap whatever you want to acquire the static charges. Now, one of the types is the positive charge, and the other one is the negative charge. Now, depending on the material you use to rub against whatever object you want to acquire the charges, you could resort to a positive or a negative charge, which are basically the two types of static charges that we have. Now, is it all the time that these charges are going to attract? The answer is no. Now that brings us to the law of electrostatics. The law of electrostatics, which governs the operation of these charges we are calling static. And I want to state it the law of electrostatics, and it states that like charges repel, while unlike charges attract. So, just like we have observed in the case of our magnets, here we work with charges, but the same case will apply if you bring like charges together, a repulsion will result. On the other hand, if you bring unlike charges together, an attraction results. Now, based on this, you can come up with fields around charges, and we will start with the obvious. If you have a positive charge, the field lines will always result from the positive charge and towards the negative charge, like that. Now, if you have a negative charge, the field will be from a north and towards the south, like that. Now, kindly note that the arrowheads point away from the charge in case of a positive charge, and towards the charge in case of a negative charge. That means that the field around the charges originate from the positive and to the negative. Now let us look at fields around different charges. Fields around different charges. Let us start with a positive and a negative charge, for example. We have said that the lines should originate from the positive and towards the negative. note the direction of the field lines. It is very important that they are originating from the positive and towards the negative. Let us look at another field of different charges brought together. In this case, let us look at a positive and a positive. We said that the lines should originate from the positive, so we expect that from every positive there will be some lines that will be originating from it and seeking a negative charge, like that. And just like the case of magnetic fields, there will be a region X somewhere in the middle that will have zero influence of these charges, and X in our case is what we will call the neutral point. Neutral because there is absolutely no effect of this field that should be felt at region X. That is why we call it a neutral point. Now, how about negative charges? If we bring negative charges close, again, there will be lines originating from some positive somewhere and towards the negative. Again, note the direction of the field lines. It is from an external positive charge somewhere and towards the negative. Again, you will also have another region X, which is also a neutral point. A neutral point. Having looked at the fields around a region, an electrostatic region, now we shall look at how charges behave. Behavior of charges. Behavior of charges on bodies of different shapes. Behavior of charges on bodies of different shapes in our next lesson. Thank you.